Okay, that's the thickness that we're given, and that's the thickness we're going to use. Okay, so we are going to find QZ at point A. Now, QZ at point A, right? So this is a non-thin wall analysis anymore. The area we are going to consider, I'm going to color in yellow. Yeah, yellow. This is the whole area that we're going to consider, right? Non-thin wall analysis. This is where we get our Q max, okay? So when that's the case, this is equal to twice of the QZ at B, which is 77.5 times 10 to the power 3, okay, plus, okay, plus. So now our width is equal to, our width is equal to 120. Our depth is going to be 30, right? Our Y bar is 30 divided by 2. So where this section that I'm doing now, I'm doing this section over here. Okay, I'm dealing this section over here. Right, the width is 120. All right, the depth is 30. The Y bar is 30 divided by 2. So from here, this will be equal to 120 times 30 times 30 divided by 2 plus by 2 times 7.5 power 3 is equal to 209. Okay, times 10 to the power 3. Millimeter cube, or 209 times 10 to the power minus 6 meter cube. So we realize that it has the biggest first moment of area, like what I was teaching you last week, right? Is the Q over T ratio always fighting against one another, right? So this is the shear stress at point A now. So it's equal to Vy over Izz multiplied by 209 times by 10 to the power minus 6, right? Divide by the thickness of 0.12. Okay. So this is equal to 209 power minus 6 divided by 0.12. Now it is 1.74. 1.742 times 10 to the power minus 3 Vy over Izz. Okay. So by looking at by reviewing the ratio, right? By reviewing the ratio, we realize that what? We realize that at the, which one is the biggest? The shear stress at B is the biggest. So tau max will occur, right? Tau max will occur at point B. Okay, given to it. So therefore, the tau max is, I think it's 75. Let me check. So this will be 75 times 10 to the power 6 will be equal to 3.875 times 10 to the power minus 3 Vy over Izz. So we can find that Vy over Izz will be equal to 75 power 6 divided by 3.875 power minus 3 is equal to 19.355. Okay, times 10 to the power 9. Okay, let me do it again. 75 power 6 divided by 3.875 power. Yeah, 19.355. Okay. So this is in Newton per meter 4. So now you can find the shear stress at point A is equal to 1.742 times 10 to the power minus 3 multiply by 19.355 times 10 to the power 9, right? So this is 1.742 power minus 3 times by 19.355 power 9 is equal to 33.716 times, correct, times 10 to the power 6 Pascal. Let me do it. 19.355 power 9 times 1.742 power minus 3. Yep, 33. Then we also know that shear stress at point C is equal to, so the ratio at point C is 2.25. Okay, so 2.25 times 10 to the power minus 3 multiply 19.355 times 10 to the power 9. 19.355 power 9 times by 2.25 power minus 3. So it's 43.549 times 10 to the power 6 Pascal. So this is how we do. As I say, I picked this example because it's a combination of thin wall and non-thin wall analysis. And what you see, like how I always elaborate, is this topic is really, really easy. But the difficult part is the what? First moment of area. It's always the first moment of area that is causing, unfortunately, causing a lot of trouble. Okay, unfortunately, causing a lot of trouble in most cases, not all, in most cases. Now I'm going to now do the same question. Okay, I'm going to now do the same question. Okay, so this is example number 3. Very similar question, the same question. But now, like how I do your term test. Like, for example, I will give a question like this, right? As I said, I've seen it before. Now, what will happen now if we have what? Vz over here, right? So this is y, this is z, right? Now Vz is over there. And then we have to construct our shear flow again, right? So when we construct our shear flow, it will look like this, right? The major web control the flow, and then it does this, it does this, right? And then it does this. No, not that direction. It goes here, right? Construct a shear flow, goes here, right? Because this over here is your major web again. They controls the flow, right? So now we are going to find the first moment of area, right? About the y-axis. Right. So now we're going to find the first moment of area about the y-axis now. Okay. So we will do that again. Point B and C are using. So I'll write down here. Okay. Point B and point C. We use thin wall, white flange analysis. And then for point A, we use non-thin wall analysis. Okay. So let's find the shear stress at point C. So at point C, thin wall, white flange. Okay, and we're going to use Q. So we know that this distance, this is the width now, and perpendicular, now this is your what? It's your depth. That's why things get confusing, okay? So if we look at point C, we only consider this area, first move area for point C, okay? So to do that, so first moment of area about the y-axis at point C now, okay? So at point C, we now know the width is 10. You see the difference, right? It's so important to label what is the width. And then we realize the depth is 30, right? So here to here is 30, right? And then if here to here is 50, so here to here is 10, right? So 60 on both sides. So 50, 10, 10, 50 is 120. So the y bar is 10 plus by 30 divided by 2. You have to be very focused on this, okay? When you do problem like this, you have to be really focused. So 10 plus by 30 divided by 2. So this will be equal to 10 plus by 30 divided by 2 times 30 times 10 is equal to 7.5 or 7.5 times 10 to the power 3 millimeter cube. So I'll do it again. The width is 10, the depth is 30 times by 10 plus by 30 divided by 2 plus bracket is yep, or 7.5 times 10 to the power minus 6 meter cube. Okay. So now again the same thing, the shear at point C. So this is equal to Vy over Izz, right? So now this is 7.5 times 10 to the power minus 6. Now the thickness is still the same. The thickness is always perpendicular to the what? The shear flow. So this is 10 times 10 to the power minus 3. So 7.5 power minus 6 divided 10 power minus 3 is equal to 0.75 times 10 to the power minus 3 Py over Izz. Okay, let me do it again. 7.5 power minus 6 divided by 10 power minus 3. Yep. 0.75 times 10 to the power minus 3. Okay. Then again, we look at point B. Okay, point B, likewise, we will use thin wall, white flange. So again, it's Q. Okay. So QY at point B now. So we know that this will be equal to 7.5 times 10 to the power of 3. Okay, plus. So now the area that we have to consider now.
Should not be now VZ and IYY instead.
Oh, you're right. Thank you. Tony, I owe you beer. So VZ over IYY. Thank you, Tony. So your QY now, right? So the area that we're going to consider is this area now, right? We now have to consider this whole area, right? So that's where we have the 7.5. And then the later part, so the width is 50. The depth is 20, right? So 50, the width, the depth is 20. And the y bar now is 60 minus by 20 divided by 2. So this will be equal to, so 60 minus 20 divided by 2 times by 20 times by 50 plus by 7.5 power 3 is equal to 57.5 times 10 to the power 3 millimeter cube. Okay, let me do it again. 60 minus 10 times by 20 times by 50 plus by 7.5 power 3, 57.5, or